Hello and welcome back to the Institute for Communication Systems at the University of Surrey. Today I'm going to depart from my usual EMC related topics and talk about reconfigurable intelligent surfaces and specifically about the multifunctional aspects of them. Actually, as you may know, the Institute for Communication Systems has developed one of the very first reconfigurable intelligent surface prototypes back in 2019. I was not part of the team back then, but since then we moved on quite a lot and we developed some new exciting prototypes. And today I'm going to show you one of them, which we will later go downstairs and measure in situ. Also, recently I have published a very exciting paper dedicated to multifunctional reconfigurable surfaces or RISs, which you can access on the IEEE Explore. It is published by the IEEE Communication Survey and Tutorials Journal. It's a very long paper, but it outlines the current state of the art and how did we get here and where do I think the RISs belong in the coming, let's say, 5 to 10 years in the era of 6G. Compared to the older RISs that we developed, you will see that this prototype is actually significantly smaller. It's only 0.8 meters in basically width and about 0.6 in height. So with this, it contains 1850 unit cells, as we call them. And remember, based on the metamaterial technology, we apply the same unit cell and just copy and paste it many times, but by varying the impedance of each unit cell, which we can do by applying voltage on each unit cell with varactor diodes, then we can change the impedance that way, because a varactor diode is nothing but a variable capacitor, and based on the voltage level applied to the varactor diode, it will give you a different capacitance. Also very important to know that we can achieve individual control of each unit cell by using the TFT matrix-like circuit, which I will talk about in another video perhaps, but it's very similar to the concept of memory charge and discharge, which you will see using one transistor memory circuits, except in this case you have a back-to-back pair of FETs. But nevertheless, this allows us to update the RIS in a cycle and without consuming too much power, because otherwise you would need 850 control lines, which is impossible. We require like multiple FPGAs, so we can do that by just simply using a matrix. Now, talking about multifunctional aspects of the RIS is where this all comes from is that the RIS in its pure form is not really sufficient to really make it into the network, because all it does is just a coverage enhancement based on a known transmit signal. You can then pre-configure it to another known receives basically location. However, what if you don't know something, like if you don't know the transmit angle and you don't know the receive angle? Well, actually the traditional RISs start to fall apart because there's no real means to deal with this. So we've added a camera here, which is a time-of-flight sensor by Lucid Labs, and we interfaced it via Ethernet to this controller. There is another controller on the back of the RIS itself. So all of this works together in a system, and that allows the RIS to actually see and scan the environment so that it can decide on what is the best configuration to have. And so the resulting system is then becomes a bit of a multifunctional system, in that it's not only providing coverage anymore, but it's actively sensing locations of users and giving them the channel where they need it. Of course, it can also adjust based on the speed of movements of users, so that we can track each user in an indoor environment or in an outdoor environment. And we can also do multi-user. So we can provide for multi-user with either multi-beam pattern, or we can switch the phase patterns of the RIS really fast. So there are two different ways of doing that. But I'll explain more in other videos about what does it all mean if you're a bit lost. We can also see a bit up close how those elements are connected together. So you see each unit cell contains a pair of varactor diodes. So one in the right hand corner and one on the bottom, and that is necessary to ensure that the reflected waves from the RIS are insensitive to polarization. So if the wave impinging the RIS is vertical, it would be reflected in the same way as if it was horizontal. In reality, most of the time you get something in the middle. So this property is actually very important to RIS designs that aim to be neutral from the point of view of radio propagation. In order to run this RIS in its multifunctional domain, we have to start the camera, and we do a bit of a clustering algorithm to figure out the location of the user. So this is all programmed using Python in the back end of the RIS controller. So I'm going to start it now. So there is a very simple script that basically runs the camera and then does some processing using clustering algorithm to effectively select the target of interest. And then it basically displays the images on the screen, which is not really necessary for the operation of the algorithm, but it's just for the demo purposes of visualization of what's actually going on inside the RIS controller. However, in reality, we're just going to output basically the bounding box coordinate, which you can see here. It's giving me coordinate at 53 degrees and 22 degrees for theta and phi. So, and then we can basically take this information and load it into the RIS configuration and reflect the radio waves towards this user at this coordinate. It's very easy to see when the camera is actually running, especially if you look at it with another camera on a white background. You can see the infrared blinking. It's not so easy to see with a naked eye, but you can still see it going a bit red in these corners. The way the camera works, it has one large transmitter in the middle, and there are 4 receivers. So it sends infrared electromagnetic waves, and then receives them at 4 different locations, and that way it can figure out the angle of arrival, basically based on a distance or difference between the received frames from each receiver. So today I'm going to show you how to do some measurement for channel propagation. Basically, we're going to use a reflective surface there and a couple of antennas, one for receive and one for transmit. And we're going to use a real-time oscilloscope by Keysight to basically get some channel characteristics such as power density spread and basic, I'll show you in a minute, phase and frequency of the channel as well. So effectively what we're going to look for today is we're going to look for a change when we use a reflective surface or configure it in a specific way to give us a desired reflection angle, whereas when we just have a random value or simply switch it off. So this is the basic measurement, and of course the first thing we've done already before I started recording is we measured this room at specific markers. So we put stickers on the floor for every 1 meter and every 5 degrees angle. So we already captured that in an empty room before we began this measurement. So then we're going to compare one against the other and see how much it's changing, because you need to average several plots to get basically a channel measurement in a specific room. Needless to say, your measurement will change if you moved to a different room. So the purpose of this is to evaluate an average indoor kind of environment where you have a large auditorium such as this. Would it be useful or good thing to have a reflective surface there, and what kind of benefit you may get from it? You can see how is the signal generated here. Basically is amplified to give us 17 dBm, and it's generated by the Keysight waveform generator. So to perform this measurement, we use a real-time oscilloscope connected to a horn antenna, and basically then the horn antenna, we measure the reflection from the environment. And when we look at the settings of the real-time oscilloscope, so rather its output, then this is really where it all comes together, because we're basically looking at the power delay profile, and that shows us all the peaks that we have in the environment. So this is effectively all the multipaths that we have. Actually, as you just saw that jump as the door has been opened, and that happened because we get a huge reflection from these glass doors and bouncing back into the horn antenna. So this is giving us the main peak, and this is exactly what we're going to monitor. Then we also have phase and frequency of this basically peak, and then all of the multipath components summed together give us the signal power. So that's effectively the setup, and now we're going to do a measurement without reconfigurable surface and with it.
We do power averaging and denoising. Don't mention it. Just say this is the PDP, this is the phase, this is the frequency.
What is the main purpose of power delay profile?
You see how multipath arrives over time.
Okay, I'll say that. The main purpose of power delay profile is to see how does the multipath adds up over time. And for this, it's average, and you can see this tall spike here, which shows you the main, basically, addition of all multipath components.
No, that's a single component.
That's a single component.
Yeah, it's the main peak is your main component, is the first one that arrives. You see, it's the first one that comes.
And where are the other components?
Well, to get other components, there's two things you need to do. You need to have a very high power. Okay, you're not gonna put me in there. You need to have a very high power and the long length of the power delay profile.
Okay.
So to have a longer length, you need to increase the number of frequency points you have.
Okay.
Each frequency point extra gives you another delay bin, which are 3.5 gigahertz. Is, I don't know, a few centimeters. I don't know what it is.
Okay. I didn't remember any of that. What's this window? This is just frequency.
That's the power spectral density.